So once again, the problem for today is we are obsessed with gradient descent and loss functions, and we're trying to estimate the average value, E of x, of some unknown dice. And of course, we've seen ways to estimate the value of a dice before, but we're like, no, we're doing it with gradient descent. All the other ways are no good anymore. We want to learn gradient descent. So we're like, let's come up with the loss function. And our first thought is, let's do this loss function that's written. Let me write it down on the blackboard here. The loss function, we're like, we have one parameter theta, so normally theta is a vector, but for us it is one number. If you want the number of parameters as 1, this is a thing in r to the 1. It's in r to the 1. And we're like, let's make the loss function how far you are from the actual average of the dice minus theta squared, right? And of course, this is a quadratic equation because this is only one-dimensional. Here is what it looks like. So this is on the x-axis is theta, and the minimum here is exactly at the expected value of x. So if we could have this loss function and we could minimize it with gradient descent, we would go down the quadratic equation, we would find the minimum, that would be exactly what we want, we'd be very happy. But just like we talked about last class, we don't know the expected value of x. If we knew the expected value of x, then we're just wasting our time, like we're done. So, of course, you cannot use this. This is all not usable. So what can you do instead? No good. Okay. And in this situation, we're pretending that in our hands, like I have in real life here, we have a mysterious dice. Let me show you the mysterious dice. So let's see if DocCam will agree to work for us today. Okay, here is the mysterious dice. Looks like you see it's got a 5 and a 1, but now I'm going to rotate it a bit. There's another 1. This is no ordinary dice, this is some weirdo dice. Why do I have such a weirdo dice? What's on it? I don't know. You're not allowed to look. Okay. Imagine the dice has like a billion sides, or imagine you have to pay money every time you look at the dice, right? Okay, so imagine something. Let's go back to the HDMI. So that's the problem in Mathematics. Will it come back? Okay. It will come back. Okay. What did you guys say? We have a nice word cloud. Open response panel. That sounds interesting. What is that? They're always changing this thing. Okay. Okay. I'm seeing a big the dice, something the dice, expected. If only we had a verb to go with the dice. What verb could we put with the dice? Okay, I guess let's read the actual things and find out. Submissions. I just got here. Yes. Okay, great. Mu x. So what is mu? What is mu? Okay, I like this. Throw dice many times to get the empirical expected value. So this is what you could do. If you weren't thinking about gradient descent, you're like, hey man, you're making it way too complicated. Forget about this gradient descent crap. Just roll the dice, add it up, call it a day. Why are we making it so complicated? The reason is so that we can do it for other things later, right? So we're going to understand what it is. Okay. Use the mean of a couple dice rolls as the expected value. Same idea. You guys are like, forget about this parameter stuff. Forget about loss functions. No, I'm doing it. We're doing loss functions. We must do them. Okay. Same idea over here in response number 5. Response number 8. Bellman equation. I don't think it has anything to do with the Bellman equation. Okay. Sample the dice every time the loss is calculated and use the running mean instead of the expected value of x. So one person wants to say, this is close. They're like, look, the expected value of x, we could replace that with replace with the sum I equals 1 to n rolls of xi divided by the number of rolls. And this thing, you could call this, some people call this the empirical mean. How do you write empirical mean? Lots of different ways to write it. Let's do it with a hat. Sometimes hats mean empirical. And the empirical mean of x. And this is like, I rolled it 10 times and I took the average. And they're like, look, you can still make a loss function. You just, inside your loss function, you replace it with this mean. And then now you have this new loss function, L theta, which is this thing. And rolls, sum of I equals 1 to n rolls of xi minus theta, all squared. Okay, this is nice. You're kind of using loss function, but you've also kind of short-circuited it, right? Like you're like, look, just forget about the loss function, just do this. That would be better, right? Like, So this is the right kind of thing. I want to tweak here. I want to do some tweaking here. You could take the average and then just do it. We want to find a way to do it with the loss function, and there's a more embedded way to kind of make the replacement gel with the loss function even more than just taking the average completely. Right? This is the classical way people do it. They're like, just take the average, stop worrying about this theta stuff. And so I'm thinking of a way that we can do this kind of replacement, but even more in the spirit of the actual loss function than this average thing. That's what I want to think about. So this is close. This is on the right track. I mean, a few people suggested just using that, which is completely throwing out the loss function. Okay. So everybody has got the right idea. I want to give you guys another chance to think about it. How could you really incorporate and have the spirit of the loss function and really go in there and try to do it? And the reason it's important to do it, and I can't just do it here. In this particular example, theta, the actual value of theta represents the expected value. But in what we want to do, theta will just be a parameter. And theta will be combined in some complicated way to give the expected value. We're going to have, when we actually do it, we're not going to have theta, we're going to have f of s comma theta. And the theta will not be representative of anything in real life. So in this particular thing, you're just take the average, set theta equal to the average. But if theta is some weird slope or weird parameter, or God forbid a neural network where it has no meaning at all, it's some weight in some deep in the fifth layer connecting neuron 27 to neuron 35, and theta has no meaning, you can't just take the average and set theta to that. You need a way to involve the training inside the loss function so that we can actually do gradient descent. So in this simple example, of course, you can cheat and just put theta equals this, but I want to find a way to embed this dice problem in the loss function so that when we put a more complicated f in, it will still work. So that's why we can't do this thing, and that's why I want you to vote again. Think about how you would take this idea of rolling the dice and incorporate that in the loss function. Okay, let me give you a few minutes to do it again. See if we can come up with some new ideas, especially for the people who just got here. So let me pause this and restart. Okay, discuss.
We haven't even defined the loss function yet. That's the issue.
I mean, should go for it. Honestly, I don't remember what other ones in the function is, so.
Yeah, that's what the average is.
I was really wondering.
Okay, I got 2 responses so far.
That's exactly. Parameter space. You sampled it and then you interpolate it. Yeah. Feels like
Okay, 20 seconds in. Put in your final idea. Your final idea might be, I have no idea, which is fine. But let's see what you guys think. Okay, let's take a look. Okay. Ooh, a ghost. That's good. Okay. Might summarize how you're feeling. Okay. Although I'm seeing some exclamation points, so some people are almost as excited as I am. Okay, let's take a look. Help. Okay, not sure. Okay. Express expected value of x as the previous loss function and use it as the input for the next. This is a little bit confusing the way it's worded, but I think this is the right idea, which is that you want to actually not just have one single loss function. You want to kind of take the idea of the gradient descent, which is improving little by little, and incorporate that in the idea of having many different things. So we're not just going to have one loss function, we're kind of going to have a lot of loss functions, and we'll use all of them sort of equally to go. Replace expected value with x, the random variable. Question mark, question mark? This is exactly what I want to do. This is great. Let's see what other people are saying. Maybe some sort of interpolation. Use an so this is the idea of an online algorithm, right? So instead of having one loss function and like minimizing it, we're gonna, as we go, we're gonna get different loss functions, and every step of gradient descent is gonna have a slightly different loss function, and hopefully on the end they will work. And it is related to the constant alpha mean idea. So this question mark, yes, great. You guys are thinking about, okay, I guess the exclamation points came in places like I'm stumped. Okay, I got nothing. Okay, great. Let's see what it is. So a few people I think are sensing the right idea here. So normally you think of, you have one loss function, and then you just do, when you do gradient descent, which is the whole point of having a loss function, is you go down the hill like this. Very nice. You fix the loss function, you go down the hill, you find the minimum. But actually, what if we incorporate into our little steps, our algorithm is going to have all these little steps anyways, because it's doing gradient descent. Why don't we use that to our advantage, and we can have a whole sequence of loss functions? So here's the idea. We are going to, when we do gradient descent, we are going to, idea. When doing gradient descent, use a new loss function, not a loose function, loss function. When I was in New York a few weeks ago, we went to the Slime Museum with my 4-year-old son. And at the Slime Museum, you have a slime name. Okay. How do you take your slime name? You take all of the vowels in your name and you replace them with oo. So the slime name for loss is loose, and the slime name for Mihai is Muhu. So think of your slime name. Maybe you'll like it. Okay. So a new loss function each time. Okay. So what do I mean by this? Here's a crappy loss function you can make. I'm going to call this the first loss function, which is simply the dice roll on the first time we roll it minus theta squared. So I'm going to roll the dice one time. Let's go to the dice roll screen and roll the dice. Here we go. Getting ready to roll. It came up a 5. So my loss function would be 5 minus theta squared. And you're like, well, that's a silly loss function. If you just optimize that function, you're going to just get 5. You're going to get theta equals 5. Okay? But I'm not going to wait until it converges. I'm going to do just one step of gradient descent with that. And then I'll change theta a little bit. And then I will take a new loss function, which is I'll roll the dice again. So the second time, I'll do a gradient descent step with a different value of theta, which is 1. Okay? So I did one step moving towards 5, one step moving towards 1. Then I'll do a third step moving towards 1 again. Then I'll do a fourth step moving towards 5. And in this way, I'm doing lots of little steps. And every time I take a step, I have a new thing I'm pointing at. Okay? And of course, none of these steps is the right answer, right? 5 is not the right answer. 1 is not the right answer. I'm doing a step towards 5. I'm doing a step towards 1. Why on earth should I reach the right answer? Well, let's find out. Okay, so the first step will be in the direction x1 minus theta squared. We'll try to minimize that. And so the first step is going to be the gradient with respect to theta of the first step is going to be 2 times x1 minus theta. Oh, times the minus 1. Okay, great. We'll put the minus in front. So the gradient is going to step in that direction. Then for my second step, I'm going to roll the dice again. Completely separate dice roll. Theta. Oh, let's write down the rule. So theta will become not arrow both ways. Theta, we're doing minus the gradient. That's gradient descent, minus alpha times the gradient of the loss, which is equal to theta. You see you have a minus gradient, minus there. So theta plus 2 times x1 minus theta times alpha. Okay. So you see the value of theta gets updated. It gets pushed a little bit towards x1 when you do one gradient descent step with the first loss function. Then we're going to repeat it. So this is like one block. We're going to repeat the block. In general, you're going to have, what are you going to have? The kth step of theta, I guess we normally just write k, is equal in the direction xk, the kth dice roll, minus theta squared. And so when we do the gradient, LK of theta, we're going to get a minus 2 xk minus theta. And then we're going to move, theta moves to theta minus alpha times the gradient, which is theta plus alpha times 2 xk minus theta. Okay, and you might recognize this rule. This is exactly the online update rule for the mean with constant alpha, right? And when we first introduced the constant alpha, I said, don't worry about it. We're just doing constant alpha just because. But now you can kind of see why. Doing constant alpha is equivalent to doing this game where instead of taking the actual loss function that you want, the actual loss function that I want is this one, which I don't know, I'm kind of doing this moving target thing where I'm like, well, okay, I don't know this one, but I can make a whole sequence of loss functions, which are sort of right on average in some sense. And by doing one step of gradient descent on the kth sample, then I'm sort of doing this shifting target, and hopefully it will converge to the actual mean. And in fact, in this situation, it does. So we know that this thing converges too close to the true thing. And you can kind of think of it as sometimes you're moving towards 5, sometimes you're moving towards 1. This dice happens to have only 5s and 1s. So you're kind of pushed towards 5, pushed towards 1. If you're too close to 5, then the pushes towards 1 will move you down a little bit. And if you're too close to 5, then the pushes, if you're too close to 1, then the pushes towards 5 will move you up a little bit. At what level is the perfect thing for you to, on average, neither get pushed up nor down? It's exactly at the mean, which in this case happens to be 3. It's exactly halfway between 1 and 5. When you're halfway between 1 and 5, the pushes towards 5 and the pushes towards 1 exactly balance out, and that's exactly what we want. So this thing, it finds the mean. And you can kind of think of this as something like the expected value of the loss function of k of theta. So on average, what is the kth loss function doing is minimized at same spot as the true loss function. And we call this loss the true loss function of theta. So of course, they're slightly different, but they have the same minimum. I won't do the proof, but in this case, it's not too hard to show. So by doing these things and having a whole bunch of them, and doing little steps to optimize the thing as this sequence goes, an online algorithm, we sort of achieve the same kind of thing we would get if we had access to the actual thing. So it's kind of like a miracle trick. We didn't know the number, and we were still somehow able to optimize towards that number. This is like pulling a rabbit out of a hat. We didn't know something, but we're still able to find the maximum. Or the minimum, I guess, in this case. We want to minimize the loss functions. Okay, so this thing I'm calling the true. Let's give this thing a name. This is the true loss function, which you will never know, but you can still get to by doing this sneaky trick that we're doing. This sneaky trick has a name. Over here, what we saw before was gradient descent. This thing is called stochastic gradient descent. Stochastic gradient descent. And the thing we did with the dice is a classic example where the reason it's stochastic is because you do one dice roll at a time instead of knowing the actual mean. So if you had a whole bunch of dice rolls and you pre-took the average, like someone suggested, pre-taking the average, that would be kind of like a gradient descent. And by doing it one step at a time with a whole stream of dice rolls, that's called stochastic gradient descent. My favorite example of stochastic gradient descent is the following. Imagine you were trying to make it to the cannon, let's say. I used to live in Toronto, and I used to say the CN Tower, but because we're at Guelph, let's say you're trying to make it to the cannon. And you don't know where the cannon is. So here's my strategy. I'm going to walk up to the first person I see. I'm going to say, which way is the cannon? And they're going to point in some direction. And then I'll take like 10 steps in that direction, and then I'll ask the next person. Okay? And now, will I always be going towards the cannon? No, because some people are wrong and will point me in the wrong direction, right? So some people, I will ask them, I'll say, which way is the cannon? And they'll completely have me turned around. I'll step away from the cannon. But as long as, on average, people turn towards the cannon, I sort of take more steps on average towards the cannon than away from the cannon. And as you get closer and closer, maybe people are more and more accurate to which way they're pointing, and eventually I'll find the cannon. So this is stochastic gradient descent, is taking lots of little steps. Each step might suck, but as long as they're sort of in the right direction, you will eventually make it to where you're going. Okay? So lots of little noisy steps. I'm going to call them noisy because they're slightly wrong, noisy steps, but on average, you're hopefully they're right. Okay, so that is the idea of stochastic gradient descent shown with a dice roll. And actually, it is exactly, in the case of the very simple problem I gave you here, it is exactly, literally the exact same thing as the online constant alpha Monte Carlo rule of taking an average. In our actual thing we want to use it for, we're going to use it in general. So we're going to have some function we want to know. It's going to be the value function, the true value function. This is the thing that we want to know. And we have some estimate for the value function. Okay, we have some estimate for the value function, the function s. And now theta are just a whole bunch of parameters that get combined with the state s to try to tell you what the value function is. This would be the loss function at one particular state. Usually when you want to learn the loss function, learn the value function rather, you don't want to learn it just at one state, you want to learn it at all the states. So you would do something like you would sum over all the states. So sum over all s, all states s. And maybe some states are more important than other states. So maybe there's some weight function you put in front. You say like, oh, okay, the really important states, make sure you know those ones. Some states that we rarely get to, it's not as important. So mu of s is the weight of state s, how important state s is. A good example in what you're doing, if you have started the lab, you'll notice that even though all the possible averages that can happen are minus 10 to 10, an average like minus 5 almost never happens. It's very unlikely that the deck of cards will be arranged in such a way that the average goes as low as minus 5. It almost always actually stays right around 0 or higher. It's pretty rare for it to be negative ever. So even though that is a state of having the deck of cards arranged so the average is minus 5 or minus 10, it's possible, maybe you want to know it, you probably don't need a huge weight on that state because it's just unlikely to be seen. So the states that you do need to care about are the ones that are really likely, things like when the average is when the deck starts, around 2. That's really important. Some of them are less important. So this is the kind of loss function we would like. This is the true loss. Okay? But of course, we don't know the true value function. We don't know the true loss function. We're going to replace this. Replace. We'll replace with an estimate. Okay. That is the idea. And that'll be stochastic gradient descent. We won't be going down the true loss function. We'll be doing some kind of approximation of this that we hope is right, and we hope that by doing gradient descent, we get to the right thing eventually. So it's some kind of generalization of our online constant alpha thing from before. Okay, I'm going to show you. Our friend DJ is going to show us a little video with these kinds of things and show us the options, but this is a good place to stop for any questions or comments. Okay, let's see. how this is going to work. Okay. Let me get this ready.
This is how AI optimizes my schedule. So I have a project coming up, so I start by listing the project and then setting a deadline.
And the theory gives much less satisfying answers. You'll see what I mean. To emphasize what's changing, date value never impacted another in data. And that brings us to the next idea.
Okay. So, I will say I've been calling the parameters theta, which I really like because it's kind of nice to see if you use Greek letters for the parameters and Latin letters for things that are like actually the states and stuff, you can kind of see the difference. The parameters are kind of made up, like we just made them up. In the textbook, and what he's going to do, he calls the parameters W. W stands for weight. So obviously theta is better, but I guess we're stuck with W here. And this little chapter here is how do we select W? This is in a video of function approximation, which is exactly what we're doing. Let's see how we select W. Turn the volume up. Okay.
Yeah. How do we select W? What we need to do is declare what makes for the
First, we need to make it slower. Okay. Okay.
in data. And that brings us to the next idea. How do we select W? What we need to do is declare what makes for the best W. Now, what qualifies for best is up for debate. But for now, let's say it minimizes something we'll call the value error. We write it like this, and it's defined like this. All this is
That's
the
exactly-
mean squared error between our approximate value function and the true.
This is exactly what we had. So v hat is what we called f. That's like what we're trying to estimate the value function as. V pi is the true value function for the policy pi, right? Okay. And exactly we have the same kind of mu s as before, summing over all the states.
Value function, and it's weighted by this. Here, mu is a distribution over states, weighing how much we care about each state. Typically, mu will be chosen as the proportion of time our policy spends at each state. Now, at this point, you may say, whoa, DJ, we got an exponentially huge space and you want me to sum over it, and you snuck in the true value, which you know we don't know? I thought you were a math communicator, not a con man. And to that I say, yeah, you're right. We'll never be able to calculate this. But despite that, we'll be able to develop algorithms that approximately optimize it. And that's pretty good. And we can do that with stochastic gradient descent, which will look quite similar to the update rule we saw in earlier videos. But we'll have to assume a few more things. First, states are visited in proportion to mu. That's reasonable since we'll be updating W as we bounce around the state space according to the on-policy distribution, which is presumably what we've chosen for mu. Second, our value function is differentiable with respect to W, which is required for calculating a gradient. And third, since we don't have access to the true value, we assume we observe a suitable surrogate for it, which we'll call UT, or the target. There'll be several choices for the target, and that'll really define the algorithm. Also, quick technical note on notation. Here I'm showing a random variable, not a value, being plugged into a function, which is not something you've seen from me before. For this, just imagine sampling a value from the random variable and plugging that into the function. That's what this means. Okay, with all this, SGD gives us a simple update rule to apply to W for each visit to a state, which is this. Soak it in, it's important. Here,
Okay, so this is, we're going to look at this rule over here, which is covered by the bar, but I'm going to rewrite it for you in our language. And it's exactly what we did with the dice roll. It's a single update rule, not for the true loss, but we're making up this estimated loss given the observation. This is like our kth loss is given sk is the state s. Then what is this thing? And the loss function again depends on the weight, not the state. We're going to approximate this thing by some surrogate thing. So this is our estimate. This is the noisy estimate for the value function. Noisy estimate for true value function. Value function at state sk. So we'll call that UK. In the dice roll, right, we wanted to estimate the mean, and we said our noisy estimate for the mean of the dice. We don't know the true mean of the dice, but let's pretend it's exactly what was on the dice when we rolled it the kth time. So So either 5 or 1. Of course, 5 or 1 is never actually right. The true answer is 3. Just like that, we're never going to actually see the true value function. It will never appear for us, but we will have some noisy estimate that we hope on average gets us closer to it. Okay, and then we're going to have minus f of sk theta, right? So we have some noisy estimate. We have our function evaluated at the state sk. And again, you'll notice there's no sum here, right? This is literally at one state. But because the state is random, on average, it's doing this mean thing, right? So the weight, how important a state is well, how often are you in that state? Like, that's what it'll be. And if that is the kth loss function, using this uk to stand in for the value function and using sk to be the point we evaluated at, then what is the gradient? The gradient with respect to theta of the loss is 2 times uk minus f of sk theta. And then there is a minus the gradient of f at sk theta. Okay? And when we do gradient descent, because we're going down the hill, this minus sign will go away. So the update rule will be theta will become theta plus the learning rate plus minus the learning rate times the gradient of the loss at theta, which will be theta plus 2 times uk minus f of sk theta times the gradient of f of sk theta times learning rate. Okay, so a couple things. One is a lot of people don't have a 2 here. I put in the 2 because my loss function was literally the squared thing. Some people put in the loss function is half of the squared thing. This is a little bit like the argument between pi and tau, which is 2 pi. It doesn't matter. Okay, so don't worry about this 2 here. If you want, you can absorb it into the alpha, into the learning rate. I will also say this kind of has the right kind of feel to it, like we talked about when we were doing the ordinary line finding before. So if our estimate, f, is higher than uk, then we're saying boost it, you're too high. Boost down, like the uk value is too high. Like we need to, if f is too high, then we go down, right? If f is too low, then we go up. So it's like we are pushing ourselves in the direction of the uk that we saw in proportion to how much the gradient is, how big the gradient is here. If the gradient is very big, we go a lot. If the gradient is small, we go a little bit. It's a little bit like this dice thing of, whatever our estimate is, if we see a 5, we go up. If we see a 1, we go down. And we're at the exact right spot. These two forces will balance out. And in more complicated situations, we saw that sort of some points matter more than other points. That's exactly saying that we go in proportion to the size of the gradient. So all the things we've done in the last 2 classes have sort of warmed us up for this thing to try to understand it. We could have written it down 2 classes ago with no preparation, but that's what it is. Okay. Questions? There is one question you should have, maybe in your brain, which is, what the hell is UK? What? And the answer is, it is a country in no longer Europe. No, okay. What is the UK, right? I said you can come up with something that estimates the value function. And again, this would kind of, coming out of nowhere, you'd be like, well, what would that be? What would estimate the value function? But actually, all the things we did before in tabular methods, when we had a big table of values, should have prepared you for what this UK is. And there's 2 different things you can use for UK. There's one, a Monte Carlo UK. What is the Monte Carlo value? UK. And there's another one, which is the temporal difference. Temporal difference. Difference. UK. And those are the 2 kinds of things you can get. And for temporal difference learning, again, you can have many steps. You can look back 1 step or many steps. But the methods of Monte Carlo or temporal difference are actually just telling you a different way to estimate an estimate for the value function. So estimate the value function at a point. Value function. That's what they both do. Okay, I guess let me write this as like a little table. So this will be the 2 rows of the table. And over here, we're going to put in the estimate for the value function. Okay. If you've been sweating away on lab 3, you might have these in your brain, at the tip of your brain. I'll tell you what they are in a second. But they shouldn't be surprises. They should be something you've seen before, and this will give us the update rule that's being used here. Okay, I'm gonna let DJ has some nice animations, so I'm gonna let him explain what they are. But any questions or comments at this point before we see the two things and fill in our table? Okay, let's fill in our little table.
Here, alpha is the step size, as we've seen before, and here is the gradient. What we're doing is, we're nudging W in a direction that maximally reduces the error from the target. So now the question is, how do we choose our target? Let's start easy. If the target is unbiased, which means the expected value of the target at state S is equal to the true value, then W will converge to a local optimum of the value error. Granted, alpha is set appropriately. Said differently, if we reran the algorithm 1,000,000 times and compared the average of each target to the corresponding true value, and those numbers were very close, then that algorithm would converge to a local optimum of the value error. And that's really nice. Remember, our value function is any differentiable function of W. So a local optimum is the best we'll get. No one out there training neural nets is finding a global optimum. An example of this is gradient Monte Carlo, where the target is just the return. To paint this algorithm for you, outside the update rule, this algorithm is virtually identical to the MC evaluation algorithm from part 3. If you recall that algorithm and understand this tweak, you know how to approximately optimize VE. Pretty cool.
Okay, so this is the simple estimate. UT equals GT. Of course, if you don't know what GT is, this is not helpful. But GT was the return in the sample we got. So this is exactly the Monte Carlo estimate we did when we started Monte Carlo. We said, if you want to know the value function, just wait until the end of the episode. And at the end of the episode, you will know what the return was. So this is a little bit like you're at the casino and you just got there and you're like, well, how good of an idea is it to place all of my money on black? Okay? You place all your money on black and then you wait a few minutes and then you see how happy you are a few minutes from now. Then you go back in time and you say, okay, that was a terrible idea. Let's not do that again, right? And then you readjust your weights and then you learn not to do that again. So the only step you need to do is wait until the episode ends and then go back and update the state that you were in given your future knowledge. If you had future vision, you could update right away. If you don't have future vision, you wait until the end of the episode and then you write down where you were and then you do the update. Some of you guys are doing this, I know, for question 1A on the lab. Wait until the end of the episode, see what the return is, look at all the states you visited on the way, and update them. And that is the first entry in our table, right? UT equals GT. So what the thing is, it's UT equals GT, or UK equals GK. UK equals GK is the return, let's say the total return from the state. The total return from the state Sk in this episode. And again, this involves waiting until the end of the episode. Another potential place you could go wrong is, remember, things that happened in the past don't matter. So if you've been at the casino for an hour and you want to know how good of an idea it is to bet one bet versus another bet, how things went in the last hour when you were here, that doesn't matter. The only thing that matters is going forward in time, how good of an idea is this bet? That is the return. And that's the Monte Carlo idea. Very simple. It really is a more complicated version of the dice roll, right? The dice roll, just you roll it and you're done. In the Markov chains we're looking at, it's not that you roll it and you're done. You have to wait until the whole episode is over. But then you see this number, GK, that's some kind of random variable, just like a dice roll, and then you go based on that. So that's the simplest thing you can do. That's called gradient Monte Carlo. So this is, if UK equals GK, it is called gradient Monte Carlo. I don't know, we don't need to write that down. Gradient, sure, let's write it down. Gradient Monte Carlo. Okay. So if you do that with UK equals GK, that's gradient Monte Carlo. Very nice algorithm, and it has lots of nice properties. The downside is you have to wait until the end of the episode. So you don't get to learn anything about your position until the end of the game. Imagine in chess, you want to know if an opening move is good or bad, but then you have to wait until the end of the game if you win or lose. Well, by that time, there's kind of a noisy signal. There's not much connection between the opening and the end of the game, it would be better if we could update sooner. Like we play an opening move and then we're like, oh crap, now I lost a knight. Like maybe that's a bad opening. So it would be better if we didn't have to wait until the end of the episode. And that is exactly what the temporal difference will do. Questions about any of that before we move on to the temporal difference one? All right, let's see the temporal difference one, how it is described over here.
But MC has its drawbacks. Waiting until the end of each episode is quite a constraint, and it can make learning a lot slower. So, what if we bootstrap? Meaning our target is something like this, where we're using a one step ahead value estimate as part of the target. Well, this will create some complications. First, it's biased. Think about right after you initialize W. Is the expected value of U with your garbage estimate inside it going to, on average, equal the true value? No. Second, and this is really weird, our target now depends on W, which is not like any typical supervised learning task. And that means the update rule is not a true gradient step. In other words, if you took this target, plugged it into the VE expression, and derived the gradient, that would be different than plugging this target into the update rule from earlier. So, that's not good. And what that means is we don't get any guaranteed convergence to a local optimum. So now what? Well, how about just do it anyway? Who needs theorems when you got high hopes, right? And so this is the thing. It's called semi-gradient TD.
Okay, so the next idea, and this might be what you were thinking, in the temporal difference learning idea, you don't wait until the end of the episode. You take one step and you just look around and you say, how good do I think the state is? That is a good estimate for how the total return I will get. And so in this one, UK is not GK. It is simply the rewards we got now plus the discounted value that we think will be. I'm using F for the value function here. So let's do F of the state, SK plus 1, given the theta that we have. So the idea is, I think the chess analogy is quite good. You're trying to figure out how good an opening is, and you play the opening moves, and then you go, let's look at the position now. How good do I think this position is? If I think this is a great position, that means it was a good opening. I should do that again. If I think this position sucks, then let's not do that opening anymore. Of course, if you've actually played chess, you might know that this is going to lead to trouble, to learning. And the reason is, sometimes you will be wrong because you're not good at chess about what is good and what is not good. So you'll be like, this is a great opening. I keep winning these games. I play this and I get to this great position, right? And then you play with some grandmaster and you get to that position again and you're like, this is a great position, I'm winning. And then the grandmaster's like, you suck, and like beats you, right? And it was because you were wrong. You thought it was a good position. You thought F was really good. And so you were like, this is great, let's move towards that position. And it turns out that position is wrong. Like your estimate for it was an overestimate. It's not actually a good position. So in that situation, all the learning you did, learning that this was a good opening, was incorrect. And that can happen, right? This is the problem with temporal difference learning, is it is potentially biased. Okay, that being said, but sometimes it works. Sometimes it works. Okay, and if, in particular, if there's some kind of mechanism by which the amount of bias is being reduced over time, then you have a hope that this might work. And in a game like chess, well, at the very end of the game, it's pretty easy to tell what's a good position and what's not. So when there's only a few pieces left, we can have a pretty accurate F. And if we have a pretty accurate F when there's only a few pieces left, when there's like a few pieces plus 1 left, then this kind of update rule will be pretty good, because it's like pointing towards the one that's pretty good, right? So we're sort of like, we're quite confident at the end. F is very good at the end. And if F is really good at the end, then at t-1, it's getting better. Right? This will be unbiased at t-1. And then if it's good at t-1, then it's good at t-2, and you sort of like filter back in time of where your knowledge is. The same kind of thing is going to happen in your lab 3, because the amount of time, the number of turns you have left, is shrinking. When there's 0 turns left, you're very confident on what the value function is. When there's 1 turn left, well, you don't start out knowing the answer, but you'll pretty quickly figure it out, because there's only one sort of step of randomness. And if you have the right idea of when there's 1 step of randomness, then you can learn what happens at 2 steps of randomness, and so on. So sort of, if you have a mechanism by which the amount of bias is reduced over time, then you can hope that this thing works quite well. And this is what people use in a lot of situations, even though it potentially has some theoretical problems. In practice, it's quite powerful. So that's the TD update rule. And by the way, the one that is written here is the one-step update. But you could easily write a multi-step update. And that multi-step update would be somewhere between the one step and the Monte Carlo. You would wait 10 steps, and then you would learn instead of waiting one step or waiting until the end. Okay, so those are the two different things you can put in for U. And once you know that, you kind of know the algorithms. I will say this one was called, what was it called? Semi-gradient. And the reason it's called a semi-gradient and not a true gradient is, you notice I took the gradient with respect to theta, and then I plugged in a function of theta, right? And if you take the gradient and then plug in, that's different than plugging in and then taking the gradient. If I had plugged in and then take the gradient, there would be an extra term over here. There would be an extra term somewhere here. And because that term is not there, it's a semi-gradient and not a gradient. And that semi-gradient is actually very good, and it helps you. It helps you orient this arrow of time of having some states that you know are more accurate than other states. You're hoping the future is easier to understand than the past. The end of a chess game is easier to know about who's winning than the beginning of a chess game. And that semi-gradient helps you with that. So that's why people use it. And that's why it is the way it is. Okay, I think I'm out of things to say about these two things. Let's watch the video and see an example, unless there's some questions. Okay. Let me see what is coming. Okay. Okay, yeah, we're going to go skip ahead to a little example that they do, which is from the textbook. Okay, yeah, so here's a nice example.
Instead,
with a 1,000 state random walk. So let's see how this works.
let's do an evaluation example from Sutton and Bardo's book. Here's the problem. It's a 1,000-state version of the random walk task from parts 3 and 4 with a few adjustments. First, we have 1,000 states labeled from 1 to 1,000. Second, if the agent is at some state, then in the next transition, there is a 50% chance it'll land with equal probability in one of the 100 neighboring states on the left side. The other 50% is for the 100 states on the right side. The very left and right sides are terminal states, each yielding a reward of -1 and 1 respectively. All other rewards are 0. Now let's visualize the true.
Okay, so this is some version of the gambler's problem, where in the gambler's problem we said if you're betting 1, you either go up 1 or you go down 1. This is a more complicated version because you don't go up 1 or down 1. You go down some random number between -1 and -100, or you go up some random number between +1 and +100. So it's like you have these 100-sided dice, and that's how much you go up or down. And the reason this is quite annoying is because if you were trying to learn about this task by learning all the states individually, most of the states are very rarely visited. Like the chance of any individual state being visited in the next roll is 1 out of 100. So you're going to need to do at least 100 tries to see one visit, right? So one transition from 342 to 349 will take 100 tries. So if you just try to learn this the traditional way by looking at every single state individually, it's going to be really slow, essentially because the number of states is starting to get quite large, and the number of possible transitions is also very large. But if you have this value function approximation thing, you can set up a thing with just a few parameters, so not thousands of parameters, but like dozens of parameters, and make it learn using the methods we just saw. So that's what he's going to show you. Okay.
100 neighboring states on the left side. The other 50% is for the 100 states on the right and 1 respectively. All other rewards are 0. Now let's visualize the true value function, where the states are listed 1 to 1,000 along the horizontal axis. The true value function is this. This is what we'll be trying to approximate. Also, this is the true distribution of states as we bounce around. This is mu, used in the VE objective. This large spike comes from the fact that we always start at state 500. Next, let's discuss the features. We'll use 10 binary functions to indicate 10 buckets. That means we form these buckets, and our feature vector will be all 0, except there'll be a 1 indicating which bucket the state is in. Next, the algorithm. We'll use n-step semi-gradient TD. The nice thing is, this includes MC if we set n high enough. In fact, let's start with MC. I'll use an alpha of this and initialize W to 0, which gives us these values. Now, if we run the algorithm over many episodes,
Okay, so I want to point out what's going on here with the function. So he said 10 buckets. That is a value function that has exactly 10 parameters. So even though there's 1,000 possible states, if you were doing this as an array, you would need 1,000 entries in your value function. Our value function that we're using only has 10 possible values because it has 10 parameters. And in this situation, the value function is very simple. The parameter tells you exactly what we think the value function is in one of these buckets. So the sixth parameter is what do we think the value is between 600 and 700. And by updating that, you see these lines move up and down. And again, we never get to see that blue line. We just see samples. And when the green line is a little bit too low, then we move up. And when the green line is a little bit too high, then we move down. And we hope that over time, we kind of get close to the true value of the blue function. And you will never get it exactly. And that's because the blue line is a diagonal line and you're using straight lines. But you hope you will get close in some sense. So let's see if that happens.
And wait, we ultimately get quite close to the VE bar optimum, which is this. So the algorithm is doing what we wanted. Now let's do TD with these choices of alpha and the number of steps. If we run it,
Okay, so before it was Monte Carlo, we were waiting until the end of the episode to do our update. So we'd say, okay, we want to update in this bucket. Let's wait until we either exit on the left or exit on the right and update either up or down, depending on what we have. In the TD update, we don't wait until the end of the episode. We wait one step. And that means that if you move to a bucket that's a little higher, then we're kind of trying to equalize the buckets. And if you move to a bucket that's a little lower, then we're trying to equalize on the other side. So each bucket is going to be some kind of average of the two buckets to the left and to the right, in some sense. Let's see what this one does.
we see that it converges a lot faster than MC. And that's the plus side of TD. But it didn't get to the right answer. It got to something off from the VE optimum. And so that's the downside. And as you could guess, setting n to something between 1 and infinity will give a solution somewhere between MC and TDs. And if you're still curious, I've included a link to the code so you can play with this yourself. But now it's time we graduate. This whole time, we've been discussing evaluation, how to value a fixed, unchanging policy. Now we discuss on-policy control with function approximation.
Okay, so far we've done, like question 1A in the lab, we have a fixed policy and we're learning the value function for that policy. But of course, once you know how to learn the value function, you can upgrade and do question 1B, which is let's learn the policy. Okay, so that's what we're going to do now. We're going to learn the policy. You're going to see there's not too many tweaks. The hard part is understanding how you learn the value function. If you understand that, it's pretty simple to update.
Here we'll be looking to discover an approximately optimal policy. Fortunately, we can lean on what we've learned already to describe things fairly quickly. Okay, like every time we've studied model-free control, we have to shift our attention from state values to action values. So, using a parameterized function, we're estimating the value of taking certain actions in certain states. Next, to keep this explanation simple, let's also assume two things. First, we'll assume the action space is not large, even though the state space is. This means we can use the max operator of action values just like we have in the past. Second, we're definitely only discussing the episodic case. The continuing case actually involves an entire rethinking of discounting, and I'm going to just avoid that. Okay, with that, we can say that control is just like the algorithms we've seen in parts 3 and 4, with one exception, the update rule, which takes this form. This is just like the update rule we just saw, except we've replaced the state value with an action value. Okay, and now we can provide a control method.
Okay, so all you have to do is before you had V, now you have Q, right? So instead of learning V of S for every state S, you learn Q of SA for every state and action. And this is exactly when we have this like kind of situation where you have to be careful on the actions you choose. You have to make sure you explore enough, otherwise you'll get stuck, right, of choosing the wrong thing over and over again. So as long as the A's are exploring, this is the kind of thing that you want to do. You have, again, choices for what you're going to put in as this UT, right? You could wait until the end of the episode, that would be a Monte Carlo, or you could just wait one step and see what it is. So those are your choices. Let's see what else he says.
Semi-gradient one-step SARSA, we set UT to this one-step target.
Okay, so this is the simplest possible thing you can do. Let me write it down. It is SARSA because we are sampling the reward and another state action. So let's write this one down. So this is SARSA. And remember, SARSA stands for ST, AT, RT, ST plus 1, AT plus 1, right? So we're at the state action ST, AT. We are at some state ST. We've chosen the action AT based on our policy. We're making sure to explore the actions enough and try all of them sort of enough times. Then we observe some reward RT and some new state ST plus 1. And then we also sample what our action would be at this new state. So sample new action. And then our update rule is going to be this. We're going to set UT to be the reward we saw plus Q, ST plus 1, AT plus 1, depending on theta, right? So this is looking one step into the future and estimating what would the reward in the future be. Let me put in the gamma as well. In all our problems, gamma has been 1, but let's put it in for completeness. It also kind of makes it visually easier to see what's going on. This one step into the future idea. And then our update rule is theta becomes whatever the old theta was plus alpha, and then we do UT minus what we think the value is now times the gradient of Q. So once again, we're updating the values of the parameters theta. If we think it's an overestimate, then we go in the direction with proportional to the size of the gradient, we move the weights up or down to try to make this smaller, right? So if it's an overestimate, we move up. If it's an underestimate, we move down. We try to get it just right. And we hope that on average, we get to the right thing. So this is exactly kind of what we did before. But before, we didn't have a gradient. We were just updating the value at every single state. Now we're updating every single parameter in this way. OK, that's the difference. Questions or comments? Yeah.
So for the gradient acts as sort of the weighting. Does
Yes.
it matter what the sign of the gradient is? Like if it's
Yes.
negative, does that mess up our? Because you were saying if our guess is too large, then it's
Yeah.
pulled down. If the gradient's negative at that point, what happens there?
Yeah. OK, this is great. I think the way to the answer to your question is to draw a picture. Let's draw a picture, and let's pretend we're learning the slope of a line. OK. So let's say theta is the slope of the line, and we want to learn theta. And there's some points over here where we're overestimating, and so we're like, let's pull down, right? So that we're moving theta down. There are some points over here, but actually, let me put them also on the same way. So these points, the difference, right? This is like the UT, this is like the Q, and UT minus Q is negative, less than 0. It's below. Let's put another point over here. So this is, again, same situation. UT minus QT is negative. These are points that are below the actual thing. But because they are on the other side, these points will actually, when we pull down over here, it's going to make the theta go up. Okay? And that's what we want. So these points are pulling on theta to make theta lower. These points are pulling on theta to make theta higher. And the difference is exactly the gradient. The gradient for these points is positive, and the gradient for these points is negative. In fact, the gradient in this situation is exactly the x-coordinate. So this point will pull the hardest. The further out you are, the harder you pull. And that makes sense, right? Because if you're a really small change in the slope will have a huge change for a really big x value. So it has sort of a lot of leverage. And it can even be negative and sort of do things in the right way. So the signs are exactly perfectly worked out to sort of like, this is like how much we blame the point for its effect. And then we're pulling on things exactly in proportion to their blame. It's a great thing to think about, and that's why I tried to do the intuition of how things were working before. Yeah, great question. Any other questions? Okay, so that's the update rule. Let me show you my example. So DJ has a cool example that is cooler than mine. So I have to show you mine first, so you don't think that I'm just lame. And my example is the... okay, let's rerun this. Connect without GPU, sure. Okay, so what is my problem? It is everybody's favorite, or maybe you're sick of it by now, the gambler's problem. And I did it in this package called Jax. And the way I did it in JAX so that I can use the gradient command. So the computer is automatically computing the gradients, and I'll show you why we need that. Oh no. What did it not like? Oh, okay, well, okay, should work. Anyway, can I run below? Run time. Run after. Okay, great. So hopefully it'll work. So first thing I did, in the gambler's problem, we know the true answer by value iteration. We did that back in like week 3 or something. Here is the true answer for the value function when you are doing the gambler's problem with 100 states and trying to find the optimal bets in a casino where you only win 30% of the time. So because this casino you only win 30% of the time, you have some kind of steepish thing like this. And it has this funny kind of character with fractal-like character of having little spikes. And that's because if you're at 50, you just go bet all your money and you kind of hope to win right away. But if you lose your bets, it takes you a long time to sort of get back up. And the optimal bet size, there is more than one optimal bet size. You can either bet all your money always, or you can do this weird thing where when you're at 50, you bet all your money. When you're at 75, you bet $25 to either go to 50 or 100. When you're at 25, you bet all your money to either go to 0 or 50. But you have these like weird in-between things you can do. So that's the gambler's problem. And here is the function that I have set up to do it. You can read these notes, but let me tell you the picture, because the picture is a lot easier. Here is the function I'm using for function space I'm using. Okay, and here it is. So here is the value function. It goes from 0 to 100. You can kind of think about it as going from 0 to 1 as well. So the value at 0 should be 0, and the value at 100 should be 1, right? So if you're at 100, you should definitely escape. If you're at 0, you definitely don't escape. And I'm going to just connect the dots between here and here with 4 line segments. Okay, so here are the possible functions you can do. You can do any 4 line segments you want to 25, 50, and 75. So you do one like that, one like this, and one like that, and then, I don't know, one like this in yellow. So you connect the dots however you want. As long as you start down here and you end there, that is a valid function in my thing. Those are the functions I want to look at. The work you would have to do is explain to the computer how to make this in terms of parameters. So you have 4 parameters in this case, and you have to explain to the computer, how do I take my 4 parameters and come up with this function? And the way I did it essentially was I made the 4 parameters are the 4 slopes. So there's a slope theta 1, there's a slope theta 2, a slope theta 3, and a slope theta 4, okay, which you can barely see because it's in yellow. But there's 4 slopes, and on the segment 0 to 25, you have slope 1, theta 1. On the slope 25 to 50, you have slope theta 2, and so on. Of course, for any 4 slopes, you might not end up at 1. So the computer takes your 4 slopes, and then it will rejig them to make sure that you end up at 1 at the end. But that is how I parameterize this thing. So I parameterized it. So I using slopes. You could have done it a different way, which would be totally fine, but that's what I did. And in the actual code, it's a little bit complicated to explain to the computer how do you take the slopes and write this function, but it is explained here using these ReLU functions. If you've ever taken a stats course and learned about splines, it's also related to that. But the nice thing is, you just tell the computer what the function is. So I have value function S of W, and you can have any complicated thing you want, because the computer will just do the derivative for you. So you can type in any code you want basically here, and it will be fine. So it's got some complicated stuff, but at the end of the day, it's some kind of thing of adding things up and doing stuff like that. So finding features, adding them up, the inner product, you see the features get hit with these normalized slope differences, whatever. It's some function. And the nice thing is, once you know the value function, the Q function, this is just like you guys did on lab 3, it is some combination of the value function with the probability you win and 1 minus the probability you win. So the Q function is written in terms of the value function using what we know. And then this is really where the magic happens, is this single line, where the computer automatically computes the gradient. So no matter how complicated your function is, the computer knows how to do the gradient, and that will make everything work really nicely. And here's some little test, I think, where I put in some particular values. I think I have a picture here. Yeah, okay, so here's a picture where I put in the slopes by hand. So I said this slope is one thing. I think I put in like some low number. Then there's 2 in a row here that are the same, that are 1, and then there's one big number, and that's what it did. The true answer is shown in green here in the back, but I just put these ones in by hand. And here, it automatically found the Q function and found the optimal bet sizes for the picture I put. So this was all by hand. And then down here, I'm doing SARSA. So how do I do SARSA? I write down the epsilon greedy thing of trying different bet sizes. And then I have, let's find the magic line. Here is the SARSA update rule, is right here. So I get the current action and the current Q value. I find the gradient. Again, this is done by magic inside the computer using the magic of automatic differentiation. I get a new state and a new action. And then this is the update rule. This is the one line where all the learning happens. W becomes W plus the learning rate times the difference in the Q function times the gradient. And that will automatically update the weights in a way so it'll push the slopes up and down in the right ways to sort of try to get closer and closer to the value. And if you look at what happens, I made it plot so I did 2,000 episodes. Let's see if I can get into the right spot here. So Google lets me do what I want. Okay. Scroll all the way to the top. Okay. Okay, so here is the very beginning. I started with the weights are all 1. 1, 1, 1, 1. Always slope 1. That was at iteration number 0. And it's a straight line. And when it's a straight line, you see you're overestimating everywhere, right? The true value is down there. And so you think it's up here. You're always doing an overestimate. So as you learn, it should hopefully push things down a bit. So again, the optimal bets are calculated just automatically using the value function. And there's a little history that shows us how close we're getting. So here is after 200 episodes, I have updated a little bit, and you see it's bent in a bit. So trying to get a little bit closer, and it's found it still thinks the optimal bets are always to bet 1. So you go to the casino, you think you should always bet 1, but it's more realistic about its chances of winning. Okay, you don't have a 50% chance of winning. I think you have a 40% chance of winning. And then over time, it's learning more and more. This is showing the actual true error versus how long we've learned. So we started with an error up here, and it has improved a bit down to there. So we started with an error of 0.05. Now we're at 0.02, and this will sort of be filled in as we go. Okay, here it is a little bit later, after 400 episodes, and it's already improving. And did it learn about any bets? No, it still thinks all the bets are 1. And look, it's improving some more. And here it improved even more. And now it's learned that actually you should bet all your money in the middle. Right? It's better to bet all your money in the middle. Our chances of winning are so low that when we're at 50, it's better for us to just go all in and hope to win now than to play around with this and wait. If we wait, we're going to be stuck in this hell of like only 20% chance of winning. We don't want to do that. Just go all in, take your chances, and try to win. Okay, so it knows the optimal bet at 50. Everywhere else, it still thinks you should bet only $1. Okay, and then it's improving. Look here, this is expanded a little bit. The error is going down. These things are moving into the right range. It's starting to be an underestimate near 50, right? And of course, we're not going to get it perfectly right because our function is made of 4 line segments. The real function is not made of 4 line segments. We're never going to get it right on. But we can get close. Okay, and here it's learning more and more about the optimal bet sizes and what to do. So it's slowly figuring out you should bet all your money. If you're at the casino and you want to leave the casino, you should just bet all your money and get it over with. The longer you stay, the more they will take your money. Okay. And at the end of the day, I think it figured out this as the loss function. Final results. It found this as the loss function, which is kind of a mix of overestimating and underestimating, which is kind of the best we can hope for. Over here, it's under a little bit. Over here, it's over a little bit. And it's kind of as close as you can sort of get to of a function that only has 4 parameters, that is made of 4 line segments. The true function has 100 different numbers in it. So we're not going to get it perfectly. That's about as close as we can sort of get. And you can see the optimal bets it found are to bet all your money between $15 and $70. It still thinks if you're between 70 and 100, you should bet $1 at a time. So that's not great. So it's not perfect, but it's starting to find the right solution. And here is the history of how it was learning over time. And I will tell you, it did not look like this the first time I ran it. I had to tweak the learning rate. Sometimes it was going crazy. It was going up and down, and that means it's not working right. But if you get the values right, this is like the best case scenario, where it's sort of always going down over time. When you do your final project, this is exactly the kind of thing you're going to be doing. You're going to be learning the value function. Of course, you don't know the true value. And then when you go to submit your answer, you're only going to submit your policy to the autograder, right? So you submit the red policy to the autograder, and the autograder runs it and says, how well did you do? And the closer your value function is to the true thing, the better policy you should be able to produce. It turns out, yeah, the not having the right policy over here makes a small difference, right? Over here, but it's still pretty good, so you would hope that this does pretty well, pretty close to the optimum, even though this thing is not perfect. Of course, it's up to you if you want to do this parameter thing, or if you want to do everything with tables, that's fine too. Okay, I think that's all I wanted to say for this example. Any questions about this one? Okay, in the last 5 minutes, let me show you the cool example that, that DJ does over here, which is called mountain car. Mountain car.
This is the mountain car problem from Sonnenbardo's book. We have a car, which I'll show as a circle at the bottom of a valley. The goal is to get here as fast as possible where the episode ends. That's encoded with all rewards being -1. Now the state space is made up of 2 continuous dimensions, and it's this continuousness that makes the state space large. The first dimension is the horizontal position, which we'll write as xt. The second is the velocity, which we'll write as xt with a dot above it. And the system evolves according to these equations, which are just a simplified physics in this valley. Note, our actions contribute to the velocity. The actions we can take are -1, 0, and 1, which correspond to throttling backwards, not at all, and forwards. For instance, if we hit throttle forward repeatedly, we'll start up the hill, but won't make it. In fact, the trick is to go backwards and then forwards with momentum to get over the edge. And that's what makes this hard for an RL agent. Okay, so how do we solve this? Well, let's use a linear function and determine our features. And this is where I deviate from the book just a bit. To understand my features, let's imagine the state space as a 2D plane, where the horizontal axis is the position and the vertical axis is the velocity. Next, I'll pick 9 evenly spaced points over this space. Now, if I have a particular point, like this, I'll look at its distances from the 9 points. Then I'll assign numbers to these distances such that low numbers imply far distances, all numbers are positive, and they sum to 1. This is just quantifying on a relative basis how close this point is to each of the points from the grid. And this works for any point in the space. This is how we'll define a length 9 feature vector for any point. Just as an FYI, this is called a normalized radial basis. I could show you the equations, but that wouldn't add much. Also, another FYI, I lied. I'm not using 9 points, I'm using about 1200, which just would have been a lot harder to animate. Okay, so how do we actually form our action value function? Well, it's written like this. What's happening is we have a dot product for each action. For example, the action value of throttling backwards is the dot product of our features and a parameter vector specific to this action. And don't let this case-wise definition fool you. This could be reorganized into a linear form, so we aren't breaking with anything that was explained earlier. And now let's apply n-step SARSA. And just to convince you that this algorithm is just like what we covered in part 4, here is the code I used, which was all copied from part 4, except I only changed it in a few spots. And thank God, because it made this video a lot easier. Okay, now to get a feel for what's going on, I'll bring back the 2D state space. But this time, I'll show the max action value. That is, the value of the best action in every state. In fact, if we flip the sign, it's an estimate of how many steps are left. At the start, it's all initialized to 0, which is incorrectly optimistic. Also, I'll include the car in the valley. Next, I'll be using 4 steps, an alpha of 0.3, and an epsilon of 0. As we'll see, exploration will happen naturally, so no need to enforce it with epsilon exploration. Okay, now begins the first episode. What's happening is, as the car explores the state space, the spots visited are updated as costly, and so it avoids them in the future, which encourages it to explore further until it completes the episode. Now on future episodes, the information gained will allow it to navigate to the end more quickly. To show that, I'll show how the action values evolve over 500 episodes. And at several intervals, I'll show how the car navigates through the state space. Let me start by getting out of the way. Okay, first, we got a new scale. Earlier, the hottest color indicated a value around 3. Now, that'll be over 100. Okay, now this is how action values evolve over the first 100 episodes. The agent is learning that having no velocity at the bottom of the valley is a bad state to be in. After this, it has a rough strategy for escaping. It just involves a good deal of ramping back and forth. Obviously, more so than necessary. So, we continue learning. And now we're a bit smarter. Now, more learning. And we're smarter. Okay, more learning. Now we're really getting the hang of it. But let's learn some more. And now this is pretty much the optimal strategy. So there you have it. We were able to guide an agent to discover a nearly optimal policy inside an infinitely huge state space. And if you like this, you can check out my code where you can explore this.
Okay, we'll stop there. I thought that mountain car example was very cool. It's a continuous state space, right? So it's not, you can't do it with the table at all. But nevertheless, you can learn about it with TD Learning. Okay, we'll stop there. On Thursday, we're going to have some brainstorming for the final project, and we'll take up the lab 3 as well. So I think that one will be useful to you guys. See you on Thursday.